This class will begin with a review of what the steady state response is to a discrete time signal. Then we'll talk about a discrete time system's response to a causal input signal, not steady state. So something that is multiplied by a u of t function, something that starts off at 0, not steady state, and then starts doing its thing at n equals 0. Then we'll talk about what it means for a system to have a linear phase response. This is a very subtle point that's often glossed over, but you need to understand this. It's a very important one, and it's one that we're going to approach from not only a mathematical approach, which is how most texts do it, but also from an intuitive standpoint. Last, we'll talk about a simple low-pass or high-pass finite impulse response filter design. It's going to be very simple. It's just going to have 3 taps on this filter, but it will let you compute what the coefficients of those taps are on the fly so that you can create a decent low-pass or a high-pass finite impulse response filter and program that into a microcontroller, say, so that you can vary the cutoff frequency on the fly. So let's begin with a review of the response to a discrete time system to a infinitely long steady state input. So last class, we talked about one particular type of steady state input, which is the complex exponential steady state input. And in general, the input looks something like e to the j at some specific frequency, omega naught times n. So let me give an example. If we have an e to the j, I'll make omega naught equal to 3. So if we put this into an arbitrary discrete time system that has a transfer function of h, e to the j omega, so that's a dtft function, what we get out is surprisingly the exact same thing as we get in. In other words, the complex exponential is called an eigenfunction. What you put in is what you get out. Most things are different, times some sort of scaling factor. And what that scaling factor is a complex number, and it's going to be the transfer function evaluated at omega equals your frequency. So in other words, since we're putting in an omega naught equals 3, we plug that in for omega. We plug that 3 into here, we get out some sort of complex number, and that is a scaling factor applied to our complex exponential. Now that doesn't seem very useful because we typically don't use complex exponentials as an input to our system, but it is useful because it allows us to, using a little bit of trig, generalize that result for a cosine input. So giving this as another example, let's say we've got a 5 times a cosine of 3 times n. And you'll notice that this frequency of 3 looks an awful lot like our previous example with a complex exponential frequency of 3. And let's put that into our h of e to the j omega transfer function. So we know what its dtft is. And you know if you put in a cosine, you're going to get out a cosine of the exact same frequency. It's just going to have some sort of difference in scaling magnitude and in phase. So we know we're going to get out something that looks like a 5 cosine of 3n. And if we added an angle here plus 25 degrees, it would be plus 25 degrees over here. But we're going to scale it by something. And we're going to change this to have a phase. And the scaling factor is going to be the transfer function evaluated at e to the j 3. We're going to take this 3, plug it into our dtft, and whatever we get out, we're going to take the magnitude, and that magnitude is what's going to scale our input to find our output. Similarly, there's going to be some sort of angle that's added to here. What's that angle going to be? It's going to be the angle of the transfer function evaluated at omega equals 3. And again, if this had some sort of angle added onto it, that angle would be added on over here too. So now you can find really fast the output when your input is steady state, either a steady state complex exponential, which is nice theoretically, but doesn't happen in the practice, or a cosine, which happens all the time in practice. And someone might say, well, what happens if it was a sine instead? If you have a sine input, you can process it the exact same way. If you like to work in cosines, what I would just simply say is that if you had a 3 sine of 2n plus 17 degrees. I would convert that to a 3 cosine of 2n. And to go from sine to cosine, it's always plus or minus 90 degrees. Electrical engineering is hard, so it's the harder of those two. It's minus 90 degrees. So it'll be 17 minus 90, which would be 73 degrees. You'd plug that into your transfer function, and what you'd get out would be that same 3 cosine of 2n minus 73 degrees. It's just going to have some sort of magnitude adjustment, and it's going to have some sort of angle adjustment. And that angle, that magnitude and its angle is just going to be whatever its transfer function is, evaluated at omega naught equals, what is it over here too? All right. That was just a little bit of scratch work. I'm going to delete that and go back to our general form for cosines up here. Now, this is actually even more general than just a complex exponential input or a cosine input. You'll notice that very frequently we put in decaying power series. It works for those too. Watch. Just to clarify these different sections, I'm going to block off each region. As before, I'm going to give this as an example. Let's say we've got a 1/2 n input to our h of e to the j omega. And the question is, what do we get out? And this is actually steady state because there's no times u of n. It's been doing this forever and ever. And all I need to figure out is, what is this power? In other words, if we say 1/2 to the n is equal to e to the j omega naught n, what is our omega naught? And once we find it, we know that our output will be equal to h of e to the j omega naught, where omega naught is whatever the omega naught corresponding to this input is, times that input. So we just need to find out what our omega naught is here. And so to do that, we see that there's this e raised to something, so we know we're going to take the ln of both sides. And by the rules of lns, if we take the ln of this entire thing on the left, that's equal to n ln of 1/2. And that equals the ln of e to the j times this. But the ln of e raised to anything, the ln just undoes the e. And so we end up with j omega naught n. And we see our n is on both sides. So we can cross that out. And now we're left with dividing through by j, omega naught is equal to 1 over j times the ln of 1/2. So if we substitute that omega naught into our transfer function, we can then evaluate this, and you can kind of see already that the e to the j omega naught, that undoes this 1 over j, and we're left with a number that we can plug into this transfer function, multiply it by 1/2 to the n on the input, and we have its steady state output. So the point of all this is that knowing what the steady state response is, knowing that this first thing is true, means that we can also find its output to a steady state cosine input and its steady state power series input. And that's great to know, but it's almost useless. And the reason why it's almost useless is that this steady state response here means that the input is on for all of time. And we know practically we're not going to have an input that is on for all of time. Now, an input that switches on at n equals 0 is called a causal input. The reason why it's called a causal input is that, pretend for a second it wasn't an input, but instead it was the impulse response of a system. Then that system would have a response to an impulse in that only starts at n equals 0. And so in other words, the output would be caused by the input. So if a system has an output that's caused by an input, it's a causal system. And then that term's just been generalized to meaning a signal too. So a signal that starts at n equals 0, we call it a causal input. And just to drive that point home, if it's not already, examples of inputs that are steady state versus causal. A steady state input is e to the j 4n. It's 3/4 raised to the n. It's 7 cosine of 3n plus 6 degrees. Those are all steady states. They've been on forever. Examples of causal inputs would be e to the j 4n times u of n, would be 3/4 of n times u of n, would be 7 cosine of 3n, and just to save time, I won't bother to write the degrees, times u of n. And these are all causal inputs. Okay, so now the question is there any way that we can find the output to a causal input? And that's in our next section.